Welcome to my channel Physics with Akash Goel. In this lecture in semiconductor, I am going to take the next topic, which is transistor. Transistor is also known as bipolar junction transistor. In short form, it is known as BJT, bipolar junction transistor. In transistor, we have two PN junctions. Already we have studied PN junction, and it has two PN junction as shown the figure. This is one PN junction, this is another PN junction. The middle region in this system, the middle region is lightly doped and it is very thin. This region is called base. One side is heavily doped and it is called emitter. Suppose this is that side and this side is emitter. The other side is moderately doped. This side is moderately doped and it is called collector. I have put symbol C. So there can be two types of transistor. One is known as NPN transistor. So emitter is N side, base is P side, and this is N side. And another possibility is PNP transistor. So this is P side, this is N side, base is N side, and collector is P side. Normally in circuits, we show the transistor something like this. In circuit symbol of transistor, we have put an arrow. This is a line. This line represents base and this represents emitter, and one point on this side represents collector. So this is base terminal, this is emitter terminal connected to the emitter, and this is the collector terminal connected to collector. And arrow is put here. In this diagram, arrow is put from this base to emitter, and in this diagram arrow is put from, the direction of arrow is from emitter to base. How the direction of arrow is decided? So arrow is put on the emitter from P to N direction. Suppose this is NPN, so base is P side and this is N side. From P to N we put the arrow, and in this the emitter is P side, the base is N side, we put the arrow from P to N like this. So this is NPN transistor and this is PNP transistor. This arrow shows the direction of current when the junction is forward biased. If this junction, emitter base junction, if emitter base junction is forward biased, so obviously the direction of current will be from P to N. So in this, the direction of current is like this, from P to N, and in this the direction of current is like P to N. So accordingly we will show the direction of arrow. So normally in circuits we show this kind of symbol. This is a circle. In that circle, this is emitter terminal, this is collector terminal, and this is base terminal. Base is represented using this line. Next topic is biasing of transistor. So how do we connect transistor in a circuit? How do we do the biasings? Whenever we connect a PN junction or something in the circuit, so we call it biasing. And how do we connect it? In normal operation, so normally in normal operation the emitter base junction is forward bias, so we connect this transistor in this circuit such that the emitter base junction is forward biased and collector base junction is reverse biased. And we need two batteries for that, because one junction has to be forward biased and another junction has to be reverse biased. So we use two batteries for this purpose, for biasing. If batteries have a common terminal and that common terminal is connected to emitter, then it is called common emitter configuration. And likewise we can have common base configuration, we can have common collector configuration. Since transistor is a three terminal device, one terminal is emitter, one terminal is base, and another terminal is collector, and normally we need a four terminal device two on the input side and two on the output side. But since it is just three terminal device, so we just take one terminal as common and connect it with this in the circuit. In this diagram I have shown the common base configuration. You can see this emitter is this part of the circuit, and this collector is this part of the circuit connected with this part of the circuit, and this base, you can see this base is common with this part and this part. One part is known as the input part of the circuit and another part is known as the output part of the circuit. And since I have written in normal operation, emitter base junction is forward biased. So for this junction to be forward biased, I'm taking example of PNP transistor. So this P should be connected with the positive terminal, and for this junction to be reverse bias, so this P should be connected with the negative terminal of the battery. So likewise the biasings are done, and we can also see why this emitter base junction is forward biased. If we do forward biasing, then in this case of PNP junction, these are holes and these are like some positive charges, and these positive charges are pushed towards base due to this kind of biasing. This is connected with the positive terminal and these are like positive charges, so these are being pushed from emitter to base. And when this charges reaches in the base region, then since base is a very thin region and we have reverse biased this, so these positive charges reach here and these are pulled by this reverse biasing, since this is negative and this negative like attracts this positive charges which reach here. So most of the holes which reach the base junction are collected by this collector. The names are given like that. So working of transistor, emitter emits large number of charge carrier. In this case, if we are taking PNP transistor, so charge carriers are majority charge carriers are whole. So emitter emits these charges into the base region. Most of this cross over the thin base region. Since this is a very thin region, most of this charge carrier will cross this and cross the over the thin base region and make collector current. So this flow like this, and this kind of biasing attract these charges, and since holes are flowing, so this holes flow like this, and this flow in the circuit also, and this makes this collector current. And some of these holes which are not collected by the collector can go through like this, and this makes the base current. So this is the base current and this is the collector current. So collector current is coming like this, base current is coming like this, and these two meet here, and from the Kirchhoff's current law or junction law, we know that in this region the current will be IB plus IC. Since IC is coming like this, IB is coming like this, so this IE will be IB plus IC. Similar thing is going on in this, and but in this the majority carriers are electron. This is NPN, and due to this kind of biasing, now for forward biasing, this would be connected with this negative terminal, and these electrons are pushed due to this kind of forward biasing, and these electrons are collected by this collector, and we have done it reverse biasing, and this reverse biasing, this positive terminal will pull most of these electrons in the collector region. So again these are the directions of current in this case, because electrons are flowing like this. Since electrons are flowing like this, so direction of current will be opposite. So IC is coming towards this collector, and some electrons are leaving like this in the downward direction, so IB will be like this, so IE will be like this, and this IE is now divided at this point. One goes like this, this is IB, and one goes like this, this is IC. I have shown some working of common collector common base configurations in this diagram, but in our syllabus mostly we have to study common emitter configuration. So in the coming slides I will be mostly dealing with the common emitter configuration in detail. Now let us take the common emitter configuration, and the transistor we are taking as NPN. So we are dealing with NPN transistor in common emitter configuration. We can make the circuit diagram like this. In this I have just shown NPN transistor like a block, and in this diagram I have used the circuit symbol of NPN transistor. So in NPN transistor, what is common? So emitter is common in both the circuits. It is part of this circuit also, this terminal is part of this circuit also, and this terminal is part of this circuit also. So it is common in both this circuit. One side is known as input, so this side is known as input circuit, and this side is known as output circuit. And again, this emitter base junction is to be forward biased. So this P is connected with this positive terminal, and this collector base junction is to be reverse biased. So this N is connected with this positive terminal. In the diagram, I have shown this battery. Strength of this battery or voltage of this battery is more than this battery. So in coming time I will discuss about why this battery has more voltage than this battery. Let us write some equations regarding this circuit. So at this junction I can write this IE is divided in two parts, IB and IC. So I can write this equation for the circuit. IE is equal to IB plus IC. And as we have discussed, all the emitter emits the charge carriers which reach the base and which are collected by the collector, and most of the charge carrier which are emitted by this emitter will reach the collector, and some of them will live through this base, and that constitute this base current, and whatever charge carrier are reaching here, that constitutes or make up this collector current. So this collector current is almost equal to the emitter current, but this base current is much less than this emitter current, or base current is much less than this collector current also. This part of the circuit we call it as input circuit. This is input part of the circuit, and this part of the circuit is termed as this output circuit. So sometimes we call this IB as input current, and sometimes we call this IC as this output current, and the ratio of this two current, beta, this is denoted, beta is written as IC divided by IB. So IC is some kind of output current and IB is some kind of input current, and this is the ratio, and this ratio is known as the current amplification factor. This ratio is called current amplification factor. And if biasing is done properly, this is properly forward biased, this is properly reverse biased, so we call this transistor in active mode. In active mode, this is properly forward biased, this is properly reverse biased, and we can define this current amplification factor beta. This beta has the value some of the order of 20 to 200, as we know that IB is much less than IC, so this ratio is huge. This is 20 to 200 of this order. We also define another parameter called alpha, and this alpha is equal to this IC upon IE, and since IC and IE are nearly equal, this alpha is like 0.95 to 0.99. this is of the order of this value, and from this relation I is equal to IB plus IC. If you divide both the sides by IC, so this is I upon IC, this is IB upon IC plus 1, and this I upon IC is 1 by alpha, this is 1 by beta plus 1. So from here we can find the relation between these two factors which we have defined for this circuit, alpha and beta. So there can be various questions on this relation also, so we must remember what is alpha and what is beta, and relation between alpha and beta can be asked in the examination. As I've said, this part is our some kind of input circuit. The potential difference between these 2 points, this point and this point, you can see this point is connected with this base, and this point is connected with this emitter. Potential difference between these two terminals is denoted by VBE. So potential difference between these 2 points or terminals is denoted by VBE. potential difference between base and emitter. So this is denoted by VBE. Again, this is denoted by VBB because this is connected with base. So we follow this tradition, we call it as VBB. This is called VCC since this is connected with this collector. And potential difference between these two terminals is denoted by V. This is connected with the collector and this is connected with this emitter. So this is denoted as VCE. Same thing we can show in this diagram also. This is VBE, base emitter, and potential difference between these two can be written as VCE. So if we want to write the values of these two, VBE, so potential difference between these two, I can write it as VBB minus potential drop on this resistance IB RB. This is the potential difference. And if we want to write VCE, VCE can be written as this is VCC minus IC into RC. Now let us see why this VCC should have more voltage than this battery. In this I have said base emitter junction should be forward bias. So that means base is at higher potential already. Base is connected with the positive terminal. So base is at higher potential already from this circuit. Now this junction, collector base junction, should be reverse biased. So for collector base junction to be reverse biased, so this terminal or this N side should be at the higher potential compared to this. So for this junction to be reverse biased, this should be at the higher potential as compared to this P side. And from here, P is already at the higher potential. If P is already at the higher potential, so we have to apply a stronger battery such that this now is at the higher potential as compared to this one, which is already at the higher potential due to this battery. So this battery has to be stronger. We can also use equations to prove our statement. This is VCE. VCE is the potential difference or voltage difference between collector and emitter terminals. But I am talking about VCB, potential difference between the collector and base junction. So this VCE, you can also write it like this: VCE, collector and emitter. This is VBE, base and emitter, plus base and collector. So this VBC is VCE minus VBE. So whatever VBE we are applying here between these two terminals is already in the minus, and we need sufficient VBC for it to be reverse biased, base collector junction to be reverse biased. So it has to be higher, it has to be sufficient. We can also see VC is equal to this VCB, which is required for the junction to be reverse biased, base collector junction to be reverse biased, plus VBE. So obviously VCE should be at the higher value. We can take some typical value. They say for example for silicon we have VBE. We need VBE equal to 0.6 to 0.7 for proper forward biasing of this junction. So we need VBE like this, and VCE, obviously this VCE must be greater than this VBE. So VCE must be greater than this 0.7, and this VCE is in the order 3 to 20 volt. So already we can see that VCE is much higher than this VBE. So VC is in the range 3 to 20 volt. So this explains why this battery has to be stronger. Let us write some more expression regarding this configuration. We can also define the dynamic resistances on input and output side. So what is the input resistance? In fact, we are writing the dynamic resistance. So input dynamic resistance. So for dynamic resistance, we have to write in terms of changes. Sometimes we change all these things. So if there is a change, then what is this ratio on input side? On input side, we will take IB as input current and this VB as input voltage. So change in input voltage VBE divided by change in the input current, and this is obtained for some constant parameter of output side, and on output side we are looking this for some constant VCE. So VC is kept constant, and if we are changing this to, then this is the input resistance. RO is the output resistance, dynamic output resistance, and on the output side the IC is like output current and VC is like output voltage. So this is delta VCE divided by delta IC, and this is done for some constant parameter on the input side, and that constant parameter is IB on the input side. One more term I am defining, which is known as transfer conductance. Transfer conductance, also known as transconductance. So what is transconductance? So in this type of terms, one term is taken from the input side and one term is taken from the output side. So it is trans term. It is noted by GM, and what I am taking here from and this is conductance. So current will be in the numerator and some voltage will be in the denominator. So what current I am going to take? I am going to take current from the output side, and this is delta IC, fluctuations or changes in IC divided by voltage from this input side, which is delta VBE, change in this. Why I am talking in terms of changes, it will be clear when we study about the amplifiers. So we are concerned about the changes, and those changes we put it here and to find all these things. Next, input and output characteristic curves. Just like in PN junction we have studied the IV characteristic, current versus voltage characteristic curves. In this situation, since we have two PN junctions, so we are drawing the two input and output characteristic curve. Input side, obviously this is for input side is for base emitter junction and output side is for base collector junction. So this is input characteristic, and on input we have IB as input current, base current, and this VB is the input voltage. So this IB characteristic is something like the forward biasing, IB characteristic of PN junction. So if VB is very small, then there is no sufficient forward biasing, and if there is no sufficient forward biasing, then IB is almost zero. So initially the graph is going along this line. It is almost coinciding with this. There is no sufficient current, and once the cutoff voltage is crossed and it starts conducting, then current starts increasing rapidly, just like the forward biasing IV characteristic in PN junction. So it is just PN junction forward biasing like situation, but here the current is of the order of microampere, and in the PN junction forward biasing the current was of the order of milliampere, because this is the base current, and base current is very small because of the very less charge carrier coming out of the base. So this is of the microampere order. So for different values of VC we can plot this. So we are plotting this graph for some constant VCE, which is 10 volt as shown in this figure. Now for output characteristic, we are taking I and V as I is IC, collector current, and voltage is VC, and we are plotting graph for constant IB. So this is constant IB 10 microampere, then 20 microampere, then 30 microampere, then 40 microampere. So as we increase VCE, so collector current first increases and then it becomes constant. So in NPN common emitter configuration, from these graphs we can define some regions. some regions in which this transistor is operating. This region, if transistor is operating like this in this region, then this region is known as cutoff region. This is cutoff region. And cutoff region, when it operates in cutoff region, when the transistor when the base emitter junction is not properly forward biased, so we say that transistor is in the cutoff region. There is no current flowing in this region. So let us write also cutoff region. When transistor is operating in the cutoff region, when base emitter junction is not properly forward biased. So it is conducting when voltage is greater than 0.6 volt. So for silicon diode, it is the normal value 0.6, 0.7. Then it starts conducting and the current starts increasing rapidly. So this is the cutoff region, and after that this region is called active region. So what do you mean by active region? When it operates in active region, active region is base emitter junction is properly forward biased and base collector junction is properly reverse biased. So proper biasing, if proper biasing is done, then the transistor is said to be operated in active region. In this diagram also, when it is not properly reverse biased, when VC is less, then as we have already seen, for low value of VCE, it is not properly reverse bias, so there is very less collector current, and in this region we call it saturated region. So when it operates in saturated region, saturated zone or saturated region, when base collector junction is not properly reversed bias. So if it is not properly reversed bias, then it is saturated. Saturated means the ability of a transistor to collect the charge carriers in collector is saturated. Its ability is saturated. It is not able to collect or attract these charge carriers in collector. And as we increase this voltage, then almost this becomes constant, because if we increase this VCE, so initially the current increases, but when it almost pulls all the charge carrier, if we increase VCE, then it starts pulling more and more charge carriers which are being emitted by emitter, and when it almost pulls all the charge carriers from the emitter, then the current almost becomes constant. Now it cannot pull more charge carriers because it is almost pulling all the charge carriers, so current will become constant. So current will become constant at some value like this. If IB is equal to 10 microampere, if we increase IB by some operation, then obviously the effect will be on IC also. IC will also increase. If we increase this again, then IC will also increase. So if we increase IB, then IC correspondingly increases. And after saturation, whatever this region is, so after saturation this region is again active region, because in active region it is active. Active means the base emitter junction is properly forward biased and the base collector junction is properly reverse biased. So we have three regions in which the transistor can operate: cutoff, active and saturated region. And in normal mode or in normal operation of transistor, we put it in active region. Next topic is transistor as amplifier, and it is the most important application of transistor. Its use as amplifier, and the circuit is almost similar to that as we have discussed in the NPN transistor characteristic, and I've shown this some alternating voltage here. This alternating voltage is some sort of signal. uh, for example, when we use mic, when we say something, then our voice enters the mic as some voltage signal, and that fluctuates the voltage of this input circuit. This VBB and VC are just for proper biasing of the circuits, and this alternating voltage which is shown here is just a symbolic representation of signals. We just, whenever we use mic or something, then whatever we say, these signals are converted into voltages, and these voltages, as we say something, fluctuate in the circuit, and these fluctuations are to be amplified using this transistor. So this transistor just amplify those signals which when we say, and it is converted into some voltages, and voltages are fluctuated, and these fluctuations are amplified using this amplifier circuit of transistor. And how do we do this? So let us just calculate these things. The first thing is, the transistor is operated in active mode, active region. What is active mode or active region? This input side is properly forward biased, and these are the biasing voltages VBB and VCC. Sometimes if we don't use this kind of symbol of AC circuit, we can also show this like this. We can also show this like this, and this represents that this input voltage is varying, and when it varies, those fluctuations are amplified by this amplifier circuit. So we can also show like this, we can also show like this, whatever we like. So as we have already written previously, those kind of equation I am again writing VBE. So this VBE we can write VBB, and now I am writing this VS, some signal voltages, minus IBRB and VCE, this is some kind of output. So this is VCC minus IC into RC. Now just take differential of these equations. So for first equation, this is delta VB, because we are interested in fluctuations. Delta VB, this is delta VBB plus delta VS minus, obviously RB is constant, so this is RB delta IB. Delta VBE, we can put this equal to 0. And how this is 0? Let us just go to that our transistor characteristic curves. You can see that VBE, this is the input characteristic curve, and you can see this VBE is nearly constant. This VBE is not changing in the active region. So in the active region, VBE is constant. So if VB is constant, there is no fluctuation as such in this VBE. VBB, in this is just a DC battery source for biasing, so this is not also changing, it is again 0. So what is fluctuation in signal voltages, which are we are interested in those? So delta VS is RB delta IB. We can also write it as the fluctuations in the input voltage or fluctuations on the input signal voltages. So this is the fluctuations in the input signal voltages. Next, for differential of this equation, delta VCE, this is equal to delta VCC minus delta IC into RC, and obviously delta VC is equal to 0. So delta VCE, we can also term it as delta V0. This is output and this is input. So delta V0 by delta VI, change in output voltage divided by change in input voltage. This is our voltage amplification factor, and this factor we denote as AV. This is the amplification factor in the voltage, AV. What is delta V0? This is minus delta IC into RC divided by what is delta VI? This is delta IB into RB. we have already defined a term called beta, and beta I defined like this: beta is equal to IC upon IB. And if you put just the values IC and IB, then we also call it as beta DC. If we define beta AC for fluctuations, then it is written as delta IC divided by delta IB. So whenever we use this AC, that means we are interested in fluctuations. Whenever we use DC, then we are interested in those absolute values. So delta AC upon delta IB. In active mode, we should remember that this beta DC and beta AC are equal for transistor acting in the active mode. These two are nearly equal. There is no difference as such, and we just write it as beta. Since both are equal, so we just write a single symbol here, beta. So this is minus beta RC by RB. We can choose RC and RB such that this voltage is amplified, and this is the voltage amplification factor, which is AV here. So AV is equal to minus beta RC by RB, and this minus represents that delta V0 and delta Vi are in the opposite phase. So input voltage and output voltages are in the opposite phase, as there is minus here. If for input voltage, if a signal is something like this for input voltage, for output voltage it will be amplified. You can see larger amplitudes. So the signal will be just copy of this, but it will be amplified, but there will be a pi phase difference between these two. So there is a pi phase difference between input and output voltage, input and output voltages. So this is the voltage amplification factor. We can likewise define some, this is also known as AC voltage gains. We can also term it as AC voltage gain or AC voltage amplification factor. There is another term which is known as AC power gain. So for AC power gain, we can write it as AP, and this AP is gain in voltage multiplied by gain in current. Gain in voltage is minus beta RC by RB. Gain in current, so gain in current, which is beta also, so beta is here, and this is minus beta square RC by RB. So this is the power gain through this transistor. Next topic, I am taking transistor as switch. In this diagram, I have drawn a graph between V0 and Vi. This is output voltage and this is input voltage, and these several regions are shown on this graph. Output voltage, as we have already shown, this is VCE and this is VCC minus IC into RC. If V input increases, then obviously all the currents increases, like IE, IB, IC increases. So IC will also increase if V input increases, and if V input increases, IC also increases, then obviously V output decreases. And this is exactly shown in this figure. As Vi increases, then with that this output voltage decreases. So Vi increases, V0 decreases. Initially it goes something like this, then it is a linear graph, and then it is just touching the axis. V0 is almost 0 finally. Since V0 output voltage is almost 0, and when output voltage is almost 0 or negligible, then the output circuit or the collector base junction is not properly reverse biased, and this is known as saturation region. Cutoff, when input voltage is not sufficient for forward biasing of base emitter junction. So when base emitter junction is properly forward biased, is not properly forward biased, so it is cutoff region. And when the base emitter junction is properly forward biased, base collector junction is properly reverse biased, then it is active and the graph is linear. So how the transistor acting like a switch? So if we operate transistor in cutoff and saturated zone, if we operate in these two zones. In cutoff zone, V output is high and V input is low. In the saturated zone, V output is low and V input is high. So we can switch this circuit from high to low when we switch the circuit from cutoff to saturated zone. So this transistor can act like a switch between this high output to low output when we use it in cutoff and saturated zone. So it is a switching between high to low, and in digital electronics we can use this kind of things. In digital electronics there are only two types of signal, high and low. High means maybe 5 6 volts, 7 volt, etc. Low means maybe 0 1, low voltage, etc. So switching the circuit between a high and a low is possible when we operate transistor in cutoff and saturated zone. So it is like switching the circuit from high to low. So here it is transistor as a switch. So let us take a problem. An NPN transistor used in common emitter configuration as an amplifier with 1 kilo ohm load resistance. So as we used RC in the output circuit, so output circuit RC is also known as load resistance. So RC or RL, this is equal to 1 kilo ohm as given in the question. RC or RL, this is 1 kilo ohm, 1000 ohm. Now signal voltage of 10 millivolt is applied. So it is signal, so we are concerned with the changes only. So this is just change. This is delta V naught or delta VB, etc. So this is just change. So sorry, this is on the input side. This is 10 millivolt. This produces a 3 milliampere change in the collector current. So delta IC is 3 milliampere. So all the things are given in terms of changes, and 15 microampere change in the base current. So this is delta IB, which is 15 microampere. The input resistance and the voltage gain are, so input resistance, so this input resistance is the dynamic resistance, dynamic input resistance. So this is equal to the input voltage fluctuation divided by the input side fluctuation in the current, which is delta IB. So this is 10 millivolt divided by 15 microampere. So this is 0.67 kilo ohm. So 0.67, and the next part is voltage gain. So voltage gain AV, this is equal to delta V naught divided by delta VI. Delta VI we know. What is delta V naught? Delta V naught is change in the this current, collector current, multiplied by RC. So RC into delta IC divided by delta VI. What is RC here? This is 1000. What is delta IC? This is 3 milliampere divided by this is 10 milliampere. So if we calculate, this is equal to 300. So correct answer is C. Next question. A common emitter amplifier circuit built using an NPN transistor is on the figure. Its DC current gain. So DC current gain, which is beta here, is 250. RC is equal to 1 kilo ohm, it is given, and VCC, the symbols have their usual meanings, 10 volt. What is the minimum base current? IB we want to know for VCE to reach saturation. So in saturation the output voltage, this VCE, is very low. So for saturation we are assuming it almost equal to 0. So this VCE is equal to 0, and this VCE is basically equal to this VCC minus IC into RC. RC is given, VCC is given, so we can find the value of IC, and this is equal to 0. So IC is equal to VCC divided by this RC, and on putting the values you can get this is 10 to the power minus 2 ampere. So this is IC, and we need to find IB. So beta is equal to IC upon IB. So value of IB is IC upon beta, and IC is 10 to the power minus 2, and beta is we are given as 250 here, so this is 40 microampere. So correct answer is A. Next question. In the figure given that VBB supply can vary from 0 to 5 volt. VCC is 5 volt, beta DC is 200, RB is 100 kilo ohm, RC is 1 kilo ohm, and VBE is 1 volt. The minimum base current and the input voltage at which the transistor will go to saturation. This input voltage is in this diagram, this is simply equal to VBB, will be respectively. So whatever given for saturation, again this VCE is 0 for saturation, and VCE is equal to VCC minus IC into RC, and IC is not given, so IC can be calculated. This is equal to 0 VCC divided by RC. So this is 5, this is 10 to the power 3, so this is 5 into 10 to the power minus 3 ampere. So we have calculated IC, and from IC and beta is already given, so we can find IB, and IB is equal to this IC upon beta, 5 into 10 to the power minus 3, and this beta from here is 200, so this is 25 microampere. So this base current is 25 microampere. We need to find this VBB and this VBE. VBB is VBE plus IB into RB. What is VBE here? So VBE, this is 1, and IB we have calculated 25 into 10 to the power minus 6, and this RB is 10 to the power 5, so this is 3.5 volt. So what is the correct answer here? Correct answer is B. Next question. In a common emitter amplifier circuit using an NPN transistor, the phase difference between the input and output voltages will be. So it is just theoretical question. Input and output voltage have phase difference of pi, as we have shown the theory. Next question. An NPN transistor operates as a common emitter amplifier with a power gain of 60 decibels. So power here is given as decibels, as we study in sound waves that the intensity or loudness of sound waves is given in decibel, and that formula goes something like this. In loudness in decibel is equal to 10 log 10 sum I by I naught. So it is just comparison of two intensities with threshold intensity. So likewise we can use this 60 decibel also. This 60 should be equal to 10 log 10, and that ratio or that comparison, and that is AP. This is power gain. So AP from here is 10 to the power 6. So AP is 10 to the power 6. This is power gain. The input circuit resistance is 100 and output load resistance is this. What is common emitter current gain? So this AP is numerical equal to beta square RC by RB. So this beta square is AP RB by RC. This AP is 10 to the power 6. This RB, which is the resistance on the input side, and resistance on the input side is 100 ohm. RC, this is output load resistance, 10 kilo ohm. This is 10 to the power 4. So 10 to the power 8 by 10 to the power 4. This is 10 to the power 4, and this is beta square. So beta is 10 square. So correct answer is 4.